Hello. Today, this video will be about interference. Okay, this is the third subtopic or third lecture series on the chapter superposition, and as you can see, there's a beautiful bubble on the screen. And what interference is, um, it's like one of the outcome of it is that you'll be able to see these little nice colorful patterns on soap. So before we start, we need to go back and throw back into the principle of superposition. So the principle of superposition says that um, two or more waves meet at a point, the resultant displacement is equal to the algebraic sum of the individual displacements. Okay, so from here, this is just another example to recap. Let's say you have a cork in between two meeting water waves. Okay, so first condition, they have to overlap. You have two waves and they are overlapping, so you get A plus A, which will give you 2A, algebraic somewhat. So you can see the cork is at a high position. Okay, and if it's negative A plus negative A, you will get negative 2A. So this is two crests and two troughs. And what happens when you have one crest and one trough? They cancel out each other. The resultant amplitude is 0. Okay, so sometimes we would also draw it this way. Okay, so let's say you have two waves. Okay, and one is amplitude A. When A meets A, you'll get 2A lor. And then here, when negative A meets negative A, you'll get negative 2A. Okay, so all this, right, is not unknown. If you don't know this, you probably didn't watch go watch the stationary wave lectures. Anyway, if let's say A were to meet negative A, you will get 0. And we have names for these things, and we call this interference. Okay, so interference is defined by the overlapping of two coherent waves forming alternating maximum and minimum. Okay, so that you get the maximum and minimum situation. Okay, so if let's say when they meet and they become larger, like this one, you can see this 2A is larger. This is what we call constructive interference, and your outcome is maximums, or we call maxima. Destructive interference is where you get minima. All right, so when we say coherent, right, this is what is meant by coherent. These 2 points, maximum then minimum, you can see this minimum will meet maximum, maximum will meet minimum. So coherent means that they have the same phase relationship. If my maximum will always meet your minimum and my minimum will always meet your maximum, it will happen all the time. So constant phase relationship, that's the key word. Okay, so non-coherent is like the second one, or suddenly you change that relationship lah. Consistent. You have a consistent coherent relationship with physics. Coherence here, right, is defined as the overlapping of two coherent waves. Okay, coherent, once again, same two waves with the same phase relationship, forming alternating maxima and minima. Later you will see the pattern because story is quite long, but this is the definition of interference. It's not the same as the definition of superposition, but is related to that. But since that there are two types of interference, one where you get crest meet crest and then you get maximum, we are going to think about what are the conditions to create constructive interference. So now I'm going to just sketch out the wavefront lah, okay? And as usual, I want to make it as pretty as possible. Okay, so while I do that, just a reminder that you can find my notes in the content library, okay, and copy it into your own personal folder. From now on, you will do it yourself. Anyway, let's say this is wave 1 and this is wave 2. You can see that they are identical. So the phase relationship, the phase difference is 0. Okay, so if the phase difference is 0, the path difference is also 0. What I mean by path difference, right, is that this wave, let me go back first. Path difference 0 means this wave and this wave start at the same point. Because they start at the same point, so there's no path difference. Okay, at the same point. Anyway, what are the other possible situations where you get constructive interference? Just rub off these two and start one cycle later. Okay, so like this one, you start one cycle later. All right, so constructive interference, sometimes call it maxima. You can also start 2 cycle later. So the delta L now would be 2 lambda. You could start 3 cycle later, 4 cycle later, 5 cycles later. It's all okay. All right. So if you want to consider the part difference, they must be in order of lambda. And then the phase difference are all in order of even pi's, because one complete cycle is 2 pi. That would be the condition, no? Okay. So the conditions here are for constructive interference. This one is frequently asked in your paper too, lah. So the first one, you need 2 waves to overlap, and the wave has to be coherent, meaning their phase relationship will always be the same. Maximum, like in this case, minimum will meet minimum, maximum will meet maximum. Okay, and they must have a path difference of wrongly already. I'll fix it later. Lambda, 2 lambda, 3 lambda. Okay. So this kind of thing generally don't memorize lah. You can visualize, then you can write already. So the phase difference for this one, for lambda is 1 complete cycle. So then this one will be 2 pi. Alright. So then your path length, if you want to write a general equation, is n lambda. Okay. And your n would be 0, 1, 2, ... 3, 4, 5. And then the phase difference will be 2n pi. Okay. Because 2 pi, 4 pi, 6 pi. General equation for even progression lah, my friends. Anyway, let's think about destructive interference. What would wave 2 need to look like to destruct with wave 1? Okay. It's like your noise cancelling earphones lah. They cancel out the noise by creating an opposite wave. Okay, so like right now I'm creating opposite waves, but this is still a consistent phase relationship because minimum will meet maximum, maximum meet minimum, minimum meet maximum, maximum meet minimum, and so on and so forth. So you will notice that in the beginning, right, the phase difference between these two, or the part difference between these two, is half a cycle. So between wave 1 and wave 2, the part difference is lambda over 2, or half a cycle, which is pi. Alright? And if you're going to look at this next one, it would be 1.5 cycle or 3 pi. And the next one would be 2.5 cycle or 5 pi. So basically, there's a difference of half a cycle between destructive and constructive. Alright? So again, all these I'm comparing. All these are options for constructive interference, okay? These are two. There are 2 or 2, whichever lah. Whichever wave 2 is, doesn't matter. Can be either one. Alright. So now we can also like write out the general conditions. Okay, you can see a progression here lah. This is an arithmetic progression. Alright, destructive interference is also known as minima. Also known as, for light, it will be dark. For sound wave, it will be soft sound or... Okay. So the conditions for destructive interference. Number 1, you still need 2 coherent waves overlapping. Because if my maximum always meet your minimum, then we cancel out all. Alright. Okay, so this one is with a phase difference of, you can see all the odd pi's. Okay, so this one is pi, 3 pi, 5 pi. Anyway, this one also will have a part difference of half cycles. So lambda over 2, 3 lambda over 2, 5 lambda over 2, 7 lambda over 2, ... You want to write the general equation, that will be 2n minus 1 pi. where n is 1, 2, 3. Okay, and then this one will be 2n minus 1 times lambda over 2. Okay, so that one would be the part difference. I just want to freeze here and just explain. These are all different variations of 2. So you don't confuse. I'm not using the red meet the green. I am using the blue, which is the first one. Let me go back to a time. Okay, there we go. I'm using the blue to meet the red, or the blue meet the green, or the blue meet the purple. That's why 2, 2, 2, they look like they're all constructive lah. Of course, if they meet, it will be, but they don't have to be. Okay, so as long as when you meet and you want to destruct, you must be out of phase or have a phase relationship of pi. Okay, so pi and 3 pi is similar lah. Okay, just some trigger for you to think about. Anyway, we're going to move on and look at the setup to show this constructive and destructive interference in the lab, or in a virtual lab, I guess. Alright, so again, there's part difference, there's phase difference. Just remember, we're looking in terms of cycles. That will make your life easier. Alright, so let's look at the demonstration. We're going to use a ripple tank. Now, in case you don't know what a ripple tank is some place inside where we have a shallow pool of water. And then here we have a motor, and the motor will vibrate up and down. It's a vibrator lah, my friends. Okay, so it's going to vibrate. Depending on what I put inside, it will create different wave patterns. Sometimes I can put a reflector here to observe the reflection of water wave. But that's not what we're doing today. What we're doing is we're going to observe interference by putting two dippers inside the water. Like this way. Okay? So let's observe what happens. So you can see, right, what is happening right now is there. Okay, so here I want to stop a bit. I'm not sure whether the desktop audio is picking up or not, but you can read the subtitles, or the link to Veritasium's video will be in the video description. So here, right, you can see the water wave when they travel. All right, you will see a position. You can see all along this line. It's destructive interference. The water will cancel out. The water's amplitude will cancel out each other. So they cancel out each other, and they cancel out each other here. Okay, here is where they build up each other. So here, although it's a bit hard to tell, here you tend to see a maximum. So there's a constructive, destructive, constructive, destructive. Okay, so yeah, tend to look again. This would be a better variation. You can see here this part is constructive, here is destructive. They cancel out. They cancel at different position. And it's a bit like if let's say you watch a concert and you happen to sit here. But I think they won't build the concert. This is where you walk lah, in your amphitheater. Do you think we'll get back to concert again? It's a weird 2020, guys. Okay, anyway, we're gonna continue. Alright. So moving on, this happens for light and for sound as well. It's at different phenomena. So this is a visual representation of diagram that you saw just now inside the pond. All right. And you can see that there are places with antinodal lines and nodal lines. Okay. So these antinodal lines and nodal lines, it's where you can get maxima and minima. Okay. So this maxima and minima happens when you have the blue one is the crest, the black is the trough. So you see all these points, crest will meet crest, blue will meet blue, and black will meet black. Blue will meet blue, black will meet black. So this entire line is maxima. If you want to cancel out, then you need to use crest and meet trough. So if you want to cancel out, then it will be black meet blue, black meet blue, black meet blue. So all this line here will be destructive interference. Okay, because when your water wave travels outwards, you will have a crest and a trough and a crest and a trough, maximum, minimum, maximum, minimum, maximum, minimum. All right, so this is the kind of pattern that you will see. All right, and you will notice that at the center between these two sources, if they are in phase, you will always get a maxima in the middle, because this both wave source would, later lah, I will show you why. Anyway, if let's say I were to observe along this line, or for light, if I put a screen here, I can see bright maximum, dark minimum, bright maximum, dark minimum, bright maximum. I get some repeating maxima, minima, maxima, minima, maxima. Okay, so S1, S2 must be coherent like source, the condition. And S1 and S2 must be in phase lah. Okay, so this is what is represented by the second half of the definition of interference. You have two waves overlapping from both wave source such that you form maxima and minima. So I'm going to pause the video a bit and ask you to think about whether you will get a maxima or minima at P, Q, R, and S. I mean, I'm going to play, but you can pause the video now and think about it. Like for example, at Q, you will get trough from one wave. This one is the trough. Meet the other trough from the second wave. So trough meet trough, you should get maximum. All right. So hopefully you can pause the video now and solve it and play. All right. So if you look at P, you will have crest meet trough, dotted line meet full line. So you have A meet negative A, which means you will get 0, which is a node. Okay. And then at point Q, you will get trough meet trough, negative 2A, antinode. Alright, so all these green points are antinode. Then all these red points are node. So if full line meet full line, dotted line meet dotted line, antinode law. Full line meet dotted line, node law. So at point R is full line meet full line, antinode, you get the maxima. And at the point S, it will be dotted line meet full line, 0 lah, you get node. Okay, so you kind of like get that pattern. So this is an example of question they can ask you in CIE. The first one, very rare lah, maybe objective. You have two dippers and we can produce identical wave on the water surface. All right. Identical also means hopefully coherent lah. So the wavelength of the wave is 1.6 cm. The phase difference between the wave produced at D1 and D2 is 0. State and explain what is observed at P. So to know whether you get constructive or destructive interference, you must look at the path difference, okay, which is 11.2 minus 7.2. What I mean by path difference is this. The wave from D1 will travel a smaller distance compared to the wave from D2, right? So the wave from D2 have to walk further lor. Walk further by how many minus? Okay, by 4 cm. So that's why if you want to find path length in terms of lambda, then your delta L will be, I think, 2.5 lambda. So all this 0.5 lambda is for constructive or destructive leh? Destructive law. So you get destructive interference at point P. But you are not done yet. You have explained, but you didn't tell me what you observe. So what do you observe? You observe a minima. To be a bit more accurate, you can say that the water wave has zero displacement, or the water is still. Observation has to be something that you can see. Okay, so now they're asking what happens if both dippers have a phase difference of 180 degree. Okay, so if you have a phase difference of 180 degree, let's say I look at this one. You see your destructive interference, if it meets the dotted line, it becomes constructive again. So if you throw a wild card in, it's like the reverse card in Uno. Reverse. Okay, so now what happens is that you will have an additional 0.5 lambda, half a cycle inside. But let's use angle lah. So when delta L is 2.5 lambda, the phase difference will be 5 pi. Alright. Okay. So with D1 and D2, new phase difference is pi. So the total phase difference will be 5 pi plus pi. So you get 6 pi. So hence, you will observe a maxima at P, or maximum displacement of your water waves at P. Alright. So what happens now when the intensity of the wave from D1 is less than the intensity of wave from D2? So previously, right, when you get A plus A, you get 2A. A minus A, 0. Now, you have A minus 0.5A, because let's say the intensity decrease. You cannot cancel out, because once the intensity is different, at destructive interference, right, one amplitude is not enough to minus the other one. So your minimum, so let's say in the first case, right, the water is still 0 displacement. Now you cannot get 0 displacement anymore. You will get less displacement, but not 0. So we start from the top first. We explain that amplitude is related to intensity. Remember, I is proportional to A square. So the wave from D1 and D2 won't be able to cancel out each other completely at P. Okay, this is because as their amplitudes are not the same. So what do you observe? So the water has a ripple of minimum displacement, but this minimum displacement is different than part 1. It is not 0. Alright, so as long as you can visualize the wave meeting or overlapping, you should be fine. So now I'm going to talk about the second show for interference, where I have a light, where I show this for light lah. So the setup for light, right, is that we need a double slit plate. Okay, this is what we call the Young's double slit experiment. So a slit is a small gap where light is allowed to pass through. Now to represent the light, right, what we'll do is we'll just draw these waves lah. It's not that we can see, we're just representing the light. And when the light passes through a slit, right, if you remember in your IG, there's this phenomena called diffraction, where the wave will spread out after it passes a slit. So the wave will pass through this one. Anyway, you have a sodium vapor lamp here because it creates light with one wavelength. Okay, I'll write that down later for you. And once at this point, the wave will split out. Okay, the light wave will split. Okay, it will spread out, and then it will meet the double plate. So normally, right, in your exam, we will only start drawing from the double plate. Okay, we already assume that when the light reaches here, they are coherent lah. Okay, need coherent source ma. So anyway, we are going to observe this pattern, but this pattern can only be observed on the screen. Okay, sometimes we need a magnifying glass. If not, we cannot see the interference pattern. Alright, so let's continue. Okay, so you kind of like get this pattern. Maxima, minima, maxima, minima, maxima, minima. Alright. So I'm going to now, at the subsequent part of the video, talk about the proof for the interference equation. The proof is not needed in your exam, but it's kind of like a nice to know, especially if you are the type that you think you want to know the equation that you are using and how it came to be. Okay, so if you look at the setup given to you, you have a double slit, okay, drawn in this way, and we are going to allow coherent monochromatic light. So monochromatic here means you have a single value of wavelength or one color. Okay. And let's say we place a screen at a distance d behind the slit, okay? And I'm now going to draw a few things just to get our bearings right. There's a wave coming out from this slit. There's a wave coming out from the other slit. And let's say they are to meet at point B. Okay this point here. But this one I already labeled the bright, dark, B for bright, D for dark along the screen already. Okay, but you know, obviously the wave below will travel further than the wave above. Now I kind of like want to find an expression for path difference. Okay, and this one, if you're a bit geometrically challenged like me, watch me draw a bunch of triangles. Okay, let's say now I take the midpoint between both slits. A bit hard to adjust the midpoint, so this is what I got, but this is actually the midpoint. Okay, and the center point will always be bright. Okay, and let's say I draw from the center point to this point. Okay, so this is again just a proof, because we need some angles. If not, how can we find distance? You know. Okay, so since both waves are, let's say wave 1 and wave 2, from the slits, from this slit and this slit will travel a distance of delta L. Okay, let's say this one is theta. The way these two lengths are very long comparatively, so this one here would be theta. If you can see, that'll be great. If you can't see, here's the proof. Okay, so I'm going to copy out the tiny triangle, which is this red triangle. Okay, and this one is 90 degree, and the reason why it's 90 degree, right, is because this wave, this length, and this length is very long. So when they are almost equal, right, this angle is isosceles. But because this angle is very small, because these two green lines are very long, so this angle is like 89.9990 lah. Okay, that's why when we draw down, this one is 90 degree. We are taking the gap separation or the slit separation as A. Okay, so slit separation is A, and right now our objective is to prove that both angles are the same. So let me label the angles first. Let's say I assign this one as theta. Okay, so this is the large blue triangle that is beside the screen. So this one will be theta. And I join, remember, this is one slit. This one is one slit here. This is one slit here. So I'm going to join this to the center, because this one is the wave from the bottom wave source. Okay, now let's consider this triangle. This triangle. Okay, I will label the vertices later for you. Let's say this angle here is alpha. So you get 90 plus theta plus alpha plus this tiny angle, let's say psi over 2. You can call it whatever you want. Psi over 2 because I took this whole angle as psi. Okay, so let's say this is N, this is M, and this is K. So the triangle MPN, the sum of the internal angles must be 180, since theta over 2 is very small. Okay, this means that theta is plus alpha is equal to 90. Okay, All right, we're going to look at the black triangle, which is our main triangle to look at. This one is 90 degree, and then you need to plus alpha, and then you need to plus this angle. Let's say this angle is beta. Okay, so you plus this one and you get 180. So you get alpha plus beta is 180. Sorry, alpha plus beta is 90. Compare lor. If alpha plus beta is equal to 90 and they are both 90, hang on, let's go back. Okay, if alpha plus alpha is 90 and alpha plus beta is 90, so theta must be equal to beta. So this angle here, theta, must be the same as this angle here, theta. Okay. This angle, beta will be equal to theta. Alright. And the reason why we need theta is because we want to find an expression for path difference. Okay. So path difference, in this case, is between the waves, and your delta L here can be calculated using A sine theta, because sine theta is delta L over A. Sine theta is delta L over A, so delta L is A sine theta. So let's now prove. At the central position, point O, the delta L is 0. Because it's an isosceles triangle, they will meet at the same point. They will travel the same distance. So bright fringe is formed. Okay. And let's say we take at point P, where the wave meet, some random arbitrary point on top. Okay. So your delta L here is A sine theta. And the second thing to look at is that you will have a bright fringe. If a bright fringe is to form at P, then what this means is that if there's constructive interference, then your delta L, again, if you remember, 0, lambda, 2 lambda, n lambda. So I will say A sine theta is n lambda. Okay? Okay, lo. Okay, number 4. Number 4, I'm going to look at the big blue triangle. Try to zoom in. Okay. So if you look at the big blue triangle, right, you will notice that I'm going to use that angle theta. Okay. And the so-called angle theta here, this big blue triangle is this one. Okay. OPMO. OPM. Alright. So tangent theta would be this side, OP divided by D. But OP is this one, right? So I want to introduce this idea of fringe separation or maxima to maxima separation. The bright dot looks like fringes ma. Okay, so X can be bright to bright, X can also be dark to dark, because it's a uniform, almost uniform representation. So let's say at point P you get the nth bright fringe. Okay, so assuming nth bright fringe at P, you get this point here, which means you will have n values of X. First bright fringe is 1x, second bright fringe 2x, n bright fringe nx. So you get tangent theta is nx over d. So for small angles, tangent theta is almost the same as sine theta. If you don't know this in maths, you can just press your calculator. Angle must be small. Okay. So tangent theta is nx over d, and our sine theta is n lambda over a. You can see from here. So I put them together, rearrange, I get x is lambda d over a, or lambda is ax over d. This, ladies and gentlemen, boys and girls, is the equation that you should memorize and know how to use. Proof no need lah. But I quite like the proof, so I show you lor. Alright, so anyway, lambda is wavelength of the wave passing through the double slit. A here is your slit separation. X is your fringe separation. Please don't confusion. So fringe separation is dark to dark or bright to bright. And D here is the separation from the slit to the screen. Okay, and all these values must be in meter. So please convert. If not, very hard to ratio. I know they are all values for length. Unless they all have the same unit, then can lah. Alright, so that is the proof for the interference equation that we will use in the examples that I will discuss shortly. Okay, but before that, I want to talk about this thing called path length. Okay, so here, right, you can see that the path length for every point is quite standard. At the center, both waves will travel the same distance, so the path length is 0. At here, at D, 0.5, that's why 0.5 lambda, so you get a dark fringe. At here, 1 lambda, bright fringe. 1.5 lambda, dark fringe. 2 lambda, bright fringe. So you get this bright dark, bright dark, bright dark, bright dark, because as you go higher and higher, the difference, your delta L become longer and longer. Okay, because this second slit has to travel further and further long. Okay, so I think you can see a pattern already. If let's say there's another dark fringe here, it should be 2.5, or the 0.5 is dark. Of course, the dark will have no meaning unless there's a bright there. So that would be 3 lambda, 3.5 lambda, 4 lambda, 4.5 lambda, and so on and so forth. So I hope you have a pattern, got the pattern. You can find this once again in the content library and copy it into your personal folder for the week. Okay, so let's do a question now. You're asked to state the principle of superposition. So this one, when two waves overlap, okay, the resultant displacement is the sum of their individual displacements. Okay. So, wow, miss this diagram so familiar. Of course lah, I copy this diagram and rub off all the labels. Why would I want to draw again? Okay, anyway, same setup. You're asked to explain what is meant by coherence. Two waves with the same or constant phase relationship. Okay, what's the phase difference of the wave meeting at Q? Q, you get a bright fringe. I know I write dark. I will amend it in a few seconds. But at Q, you can't get a bright fringe. So if you want to have a phase difference discussion, right, all the bright will be even pies. Okay, even pi, because they have to be in phase ma. And then all the dark will be odd pies. Okay, so that means at Q it will be 2 pi. So you're like very happy. You write 2 pi and then you notice, walao, theta. Okay, I'll change to 360. Okay, next part. Calculate the path difference in nanometer of the wave meeting at P. So at P you have a dark fringe. Okay, start again, half lambda, 1 lambda, 1/2 lambda, 2 lambda. So at P, your path difference is 1/2 lambda. So we're going to put 1/2 lambda there, and we already have lambda, 610 nanometer, so just substitute. You know what? In this whole chapter, if you can count stationary waves, interference, you know the pattern and you can count, all the questions are very easy. You don't know the pattern, then you'll be confused lor. Arithmetic progression only ma. Okay, so anyway, you will get 915 nanometer. And part 3, you're asked to determine the distance between the two slits, which is A. So this one, we need to use the interference equation. Lambda is AX over D, or A is lambda D over X. Because I prefer to rearrange before substitution. This is the wavelength. The screen is 2.7 meters apart. So let's plug that in. And let's think about the value of X. How many X are there in 22 mm? So because I'm being nice here, I'm drawing the arrow between every bright fringes form. We call it fringe because of that pattern. Anyway, so here is X, because bright to bright is X, bright to bright to X, bright to bright is X. So this is 4X. Okay, so 22 mm over 4 times 1 over 4. Alright, so that will get you your A pretty easily. Okay, so next. A higher frequency of visible light is now used. State and explain the change on the separation of fringes. So you know when frequency increase, lambda will decrease because V equal to F lambda and V is constant. It's light ma, all light travels at the same speed. Okay, so from X is lambda D over A. When lambda decrease, X will decrease. During exam, you don't draw arrow like me, you write full sentences. Okay, anyway, part 5. The intensity of the light incident on the double slit is now increased. Okay, without altering the frequency. Which means previously, let's say it's A plus A, you get 2A. Now 2A plus 2A, you get 4A. Yay! So the bright fringe appears brighter. Because now we are not increasing just one, we are increasing both. Okay, increasing the light hitting the double slit, so we're increasing both. But the fringe separation stay the same. Dark fringes already cancel out, will still stay the same. So 1 mark for each statement. Okay, last example for the video. State the relationship between intensity and amplitude of a wave. Intensity is proportional to amplitude square. And this one is a similar drawing. It's just that they throw out all the other situations. The other setup. It is a microwave source, so it's still a light. You get a series of maxima, minima, interference. The wavelength is 6 cm. So calculate the frequency of microwave. You can use V equal to F lambda. It's a bonus question. Okay. So where you had the screen, now you put a detector lah. Then the detector will detect maximum, minimum lor. Describe and explain the intensity of the microwave detector at X. So same idea. We need to find the delta L first. And once we find the delta L, we find what multiple of lambda it is. And that will tell us whether it's constructive or destructive. So from here, delta L is 0.18 meter divided by 6 cm is 3 lambda. Good news. 3 lambda means this is constructive interference. If let's say you cannot remember, you just draw lor. So this is a beautiful wave. And 3 lambda 2, 3. So meet this red color wave. Looks constructive to me lah. So the microwave detector at X is maximum intensity. Alright. Okay, and that's all the time we have for today. I've forgotten to edit this part out, and I will see you in class or the next video. Bye bye.